So the full name of map is maximum posterior estimation. So posterior here is referred to this condition probability. So then, as the name suggested, maximum a posterior estimation is trying to find out a model M which has the largest posterior probability, namely the conditional probability M given D. So this is called map estimation. So let us write down M is map estimation. It's the model which maximizes the posterior distribution that is given the conditional probability of M given D. And then, according to the base rule, we can copy the base rule here, right? So it is equivalent to maximize this marginal probability multiplying the conditional probability D given M and divided by the marginal probability of D. So this is a simple copy of the base rule on this right-hand side. And as we mentioned in the last class, this marginal probability of M is usually called prior. And later we will discuss why it's called prior, why it's called prior. It's actually a way to encode our prior beliefs or knowledge or even bias according to the range and possibilities of model. And then this term, the conditional probability of observed data D given the model M is usually called likelihood. It is intuitive because this is actually determines how likely given specific model M D is produced. Obviously, the larger this conditional probability, the more likely that the data is produced by this specific model M. So actually, we can see that the posterior probability is actually the prior probability of M multiplied with the likelihood and then divided by the marginal probability of data. So we know that and map estimation is actually to find out the best model, namely it has the largest posterior probability. So we're trying to maximize this. As we just discussed, this marginal probability, PD, is actually constant to M. No matter how you choose M, this value doesn't change. Then it means when we do the maximization, we can throw out this PD because this is just a positive constant. So now this maximization becomes what? Because maximizing the product between the prior with the likelihood. So this is a way, this is the most common way to find out the map estimation. So we don't need to calculate this. Another point, which you may have you may not have feeling at this point of time because you don't know how difficult to compute this marginal probability PD. In a senior, it's actually an efficient way to compute the marginal probability of the data. Is actually a cutting-edge research in machine learning. So it's very difficult to compute. But fortunately, if we want to do the map estimation, we actually do not need to concern this computation. We can just throw it out. So this is a map estimation. Then what is maximal likelihood estimation? So no, this is prior, right? And this is the likelihood. So what is maximal likelihood estimation?
The greatest value for the likelihood.
Yeah, as the name suggested. So another very commonly used, if you guys have taken some statistical classes, maximum likelihood estimator is kind of everywhere word. We're very familiar with that. So maximum likelihood estimator simply discard the prior term here. So it only maximizes the likelihood, namely the probability that the observed data D given the model M. So this is called maximum likelihood estimation. So it actually ignores the influence of the prior. So now we can imagine in what kind of cases maximum likelihood estimation and map estimation become equivalent.
When the model probability is equal.
Yeah, exactly, right? So you don't assume any preference on some specific model. You assume, okay, all possible model values are equal, likely. So from a mathematical term, it means that the prior of M follows a uniform distribution. So what is uniform distribution? So suppose this is a range of your model, right? And then assume the probability density or probability that M takes any value inside this range is equal. That means the prior probability of M is kind of constant to M. So in the maximization, we can throw it out. And it is equal to the maximum likelihood estimation. So this is one obvious case that we can consider map estimation and maximum likelihood are equivalent. But later today, we'll discuss another case when the maximum likelihood estimation and map estimation are becoming similar. It's actually asymptotically closer. So this is two frameworks to compute or to find out a best model given a set of data. But a commonly used assumption we should keep in mind is that our data usually consists of a set of data points. So let us denote as x1 to xn. For example, suppose your model is a probability that when you toss a coin, you can see a head. To estimate this model, what should I do? I use my coin and I flip it and see the result. Then I get x1, right? And I flip again, I see another result, maybe tail, I see it again. And I flip it like n times, I got n results. This consists of data. So data is usually not a single data point. It actually consists of a number of data points. And then an interesting problem is that, or an important problem is that, how can we compute the likelihood? Namely, given the model, what's the likelihood or what is the probability of the data? This actually needs us to think about what is the probability of this set of data points, xn, given M. And very commonly used assumption is that we assume, given this model, the joint probability of all the data points, they are independent. Namely that the joint probability is equal to the production of each probability of each data point. So basically, it can be written as Px1 given M, Px2 given M, until Pxn given M. So if you write it in a concise way, it can be written as production. This is a production symbol, right? I from 1 to n, Pxi given M. So this assumption is really called IID assumption. Independent, identically distributed. So independent is easy to understand because we assume their joint probability given M is the production of their marginal probability given M. Right? So this is the definition of independence. Right? So for two random variables, we say A and B independence, meaning that the joint probability of A and B, here actually more accurate to use intersection, is PA times PB, right? Similarly, in this case, if you assume these n data points are independent, then their joint probability should be the production of the probability for each data points. And identically distributed, what does it mean? It means that the likelihood of each single data point has the same form. for example, the normal distribution, like the Gaussian distribution. Obviously, when you have observed different data points, this likelihood has different values, but the function form, is exactly the same. This is called identically distributed. So we combine independent and identically distributed, we call it IID assumption. So this is a very widely used assumption in our practical data mining and machine learning tasks. So now let us consider, suppose our observed data is a set of data points x1 to xn. If we want to do the maximum equals 2 estimation, we actually, from here, right, we copy here, that estimation would be maximize the prior of m, Pm, right, and the data likelihood, dm, and we know that the data consists of a set of data points x1 to xn. And then according to the IID assumption, we know that this likelihood is actually a production term here, right?
So what does that last line say? Because I can't really read the that first symbol.
You can now
The
read
line
this or this
below,
one?
that line, yes.
Yeah, this is a production symbol.
Okay.
Meaning it's a simplified way to write the production of set of terms. If you don't like it, you can stick to this. So maybe my writing is bad. So here, this is production. Production from term 1 to term n.
Okay.
And then inside this production, we can simply write this. So they are totally the same thing. Just a way to make you feel convenient. You do not need to read this long production. So now we just replace this with I replace the likelihood with this production according to the IID assumption. So now we have the prior times this production, right? So here is px1 given m to pxn given m. Because of the IID assumption, these two are the same. And now to maximize this, the Euro method you need to calculate the gradient with respect to this production. And if you have a lot of data points, you have to calculate the gradient with respect to this long production, which is quite tedious and difficult. Then what is the common use trick for this? Yeah, take logarithm. Because logarithm is a monotonic increasing function. So when you take logarithm over the objective function, it won't affect the optimum value that makes the function maximum. So to find out the map estimation, it is equivalent to find out the maximum of logarithm of the production between the prior and the data likelihood. PM here, I just copy this term. Qxn, given m. And what's the benefit of taking logarithm? Because logarithm converts the production to a summation. So now we can just write it as it is totally equivalent to the logarithm of the prior plus this summation, logarithm of px1 given m plus plus logarithm. When you have this additive structure, it's very easy to parallel the operation. For example, you have the first CPU core to compute the gradient for this log likelihood, and second to compute the second, and third to compute the third. Then you can do it in parallel. So this trick is called logarithm, log likelihood. So similarly, if we want to estimate the maximum likelihood estimation, we also take logarithm over likelihood. This is called log likelihood. So it is take logarithm over the likelihood. And similarly, because the likelihood is a production of this bunch of likelihoods for each single data point, right? So we take logarithm, you actually end up with this. And you maximize this to find the best model. So this is a common used trick. Any question at this point?
In the map, can we just do logarithm on the likelihood and don't do logarithm on the point?
If you take the logarithm, you should take logarithm over the entire objective function. So what is the entire objective function? It is a multiplication of the prior, multiplication between the prior and the likelihood, right? When you take a logarithm for this production, it immediately becomes a logarithm prior plus logarithm of log likelihood. You cannot avoid this. Right? You cannot do that. Do things like you multiply PM with the logarithm of data likelihood. This is actually not allowed. Why? Because when you do this, you cannot guarantee the optimal value of M keep unchanged. Right here. Only when you take log over the entire function, you can guarantee. You can guarantee, okay, the maximum value won't change. But you take logarithm over part of them, then change will happen. Any other question? Okay. So now let us go back to the base rule. And I want to talk a bit about this framework, its usage in the artificial intelligence research. So again, this posterior distribution, right? The model M given observed data D is proportional to the prior of M multiplied with the likelihood. And also keep in mind there's some tiny difference here. If M is discrete, then this is a discrete probabilities. If M is continuous, this is a continuous density function. But basically, they are in the same framework. The computation, the only difference is in computation. If you have discrete probabilities, you need to do the summation. If you have a continuous random variables, you have to do the integral. But they are exactly in the same framework. So, but just keep in mind their difference, this tiny difference. So we denote this conditional probability, that is M given D, as the posterior, right? And this one as the prior. And this is likelihood. So you can see likelihood comes from the data. Right? Prior defines our prior preferences about the model. So now we can contrast it with our human learning procedure. So when you learn something, before learning anything, right? You have some rough knowledge, you have some rough recognition, or even you have some bias toward the thing you're interested in. So that corresponds to the prior. And then when you look at some data, when you begin to learn something, namely you are looking at some data. So data here is referred to like books, like newspapers, like homeworks, even the chatting with your friend. You actually absorb some new knowledge from the outside environment. And then in biological meaning, there are some internal mechanisms that combine your prior recognition, prior knowledge with the new information you obtain from external environment. And then you update your beliefs about the things you're interested in. So this is very similar to human learning procedure. The difference is that this is a mathematical framework. Actually, until now, we don't know the exact human learning procedure. But in artificial intelligence, our task is to mimic human learning procedure. with some mathematical framework. So Bayes' rule actually provides such a framework. We can use prior to encode our prior beliefs or knowledge, and then to combine. Then we extract some information or knowledge from some outside data, and then with this framework, we can combine the prior with our new knowledge extracted from data to update our beliefs, which are represented by posterior. So you can see here, Bayes' rule is also a very important way or framework for artificial intelligence development. And hope in your future artificial intelligence course or future learning artificial intelligence, you can sense the existence of Bayes' rule. So now let us go back to our data science domain. So we are going back to the data science domain. So here again, M is model and data are the observed data. So if we follow the exact Bayes rule, remember the core task for data science is what? Is to given a set of observed data, usually noise data, to infer the underlying data pattern, namely the model M. Right? This is a core task for the data science. And there could be many ways to do this inference. And this process, I can tell you there are a lot of words to represent the same meaning. So this process, sometimes it's called inference. And sometimes it's called training. And sometimes it's called model estimation. So don't be confused by these jargons. They are telling the same thing. So basically, how can you recover some hidden patterns from the observed data? So there could be many ways of doing this. And if we want to do this by computing the posterior probabilities, that is the conditional probability of the model M given observed data D, this method is called Bayesian inference. Because this procedure is called inference, right? Because it follows the Bayes rule, so it's called Bayesian inference. And there could be many other ways to do the so-called inference, like maximum likelihood is another type of inference, but does not account for the prior. So Bayesian rule consider the prior and the likelihood and combine them together to compute the posterior probabilities or posterior distributions of the model M. So what's the benefit for this? What's the benefit for using the Bayesian inference framework? We can contrast it with like maximal likelihood estimation. Maximal likelihood estimation, okay, first I just want to find out a single point, M, rather than a distribution of the model M. And second, I do not care about the prior. I only find out the model which maximize the likelihood. In contrast to this very widely used estimation method or inference method, what is the benefit of Bayesian inference? So first, here I want to list a few benefits. First, we can do the diagnosis with the prior information. So let me give you an example. Suppose we want to measure the average height of the students in some university, for example, in the U. Okay. So the model will be the average height of the students in the university, in a university. And suppose I have collected a set of data, right? Namely, a set of heights from a bunch of students. From Bayes rule, I need to assign prior over M, right? Over the average height. How can I assign the prior? For example, I assign the prior of M to be a normal distribution with the mean expectation to be like 66 inches. This is our common sense knowledge about the average height for a fully grown up person. And variance variance. The standard deviation will be 6 inches. So the variance will be 36. So this is our prior. And then we can define the likelihood, right? Given this average heat, how the observed data is produced, say from another Gaussian distribution. So right now we do not consider detail. But then suppose we are given such kind of data and we use prior and the likelihood to find out some map estimation. So map estimation would be maximize the prior multiplying with the data likelihood. Then what happened is that I found that the best model says that the average heat is 20 inches. What's wrong here? It's ridiculous, right? Why it is ridiculous? Because it is so far away from the prior distribution. In our prior distribution, we expect that a fully grown-up person should be on average 66 inches. Right? But after we collect the set of data, we do the inference, we do the Bayesian inference. Of course, here we only focus on map estimation. A single point, we found out, okay, the best model is only 20 inches. So we know that there must be a problem here. It could be the problem on your modeling of the data likelihood. Maybe your data likelihood is not reasonable at all. Or maybe the collected data is problematic. For example, some hits are measured by feet, and some hits are measured by inches. And then when you do an estimation, you found, okay, the 20 inches is definitely problematic. But someone may ask, I do not need to consider the prior. We can come out the same conclusion as well. Say, if I do the maximum likelihood, I found an even ridiculous number like 5 inches. Then according to my common sense knowledge, it must be problematic. Then I look up the data, I look at the model. But this is just a very simple case. And by the way, when you use your common sense knowledge to diagnose this problem, you are still using some prior knowledge, right? Because in your prior knowledge, prior mind, you know that a fully grown-up person won't be like only 20 inches or 5 inches. But in practice, in many complex problems, without such kind of prior, actually you have no idea about this prior. What is the prior? You must construct this prior from other experts, or construct prior from very high quality data. If you don't construct this prior and directly use other methods to find out the best model, you actually have no idea whether your learned model is valid or not. So that's the benefit of incorporating prior knowledge. Because by contrasting what you have obtained from the posterior with the prior, you may find out the potential problems here. This is the first benefit. And the second benefit is that Bayesian inference can account for all possible models. Right? Doing this can allow us to compare different models. Say, suppose I have two models, M1 and M2. I want to know which one is better. Can we do it in the maximum likelihood estimator? You can only do this when M1 is the MLE estimator, M2 is not. Okay, I can conclude that M2 is worse than M1. But what if M1 and M2 are both not the maximum likelihood estimator? How can we compare them? In Bayesian framework, we can compare them through the posterior probability. Say, if this ratio, the posterior probability of M1 given posterior probability of M2 is 2, then we can roughly conclude that M1 is twice better than M2, right? Or M1 is twice likely than M2. So this is another benefit. That it can benefit, the Bayesian inference can provide a principled way to compare different models. And third benefit, what's the third benefit? Again, Bayesian inference concern a probability distribution of the model M given observed data D, not only on a single point. Of course, the map estimation can be considered as a special instance because the map estimation only consider one single point as well. Right? But in a most general framework, the Bayesian inference framework, actually we're considering the distribution of the M. Then what does it mean? It means that we can do the model average. When we use the learned model from data to prediction, we actually do not only need to use one model, we can use all types of models. How can we do that? So suppose given a model, I want to predict the label or predict whatever, something related to a new data point X. And suppose this is through from a prediction function or X given M. And in maximum likelihood estimation, I need to first find out the best model through maximizing likelihood. So let me denote as MLE, right? So the prediction would be this prediction function given the MLE estimation. But with the Bayesian inference, what can we do is that we can do the weighted prediction. So the weighted prediction is very similar to expectation. How can we do that? We just sum over a possible M, right, in a sample space and use each model to do the prediction and then weighted by what? By the posterior probability here, right? So this way, we are doing model average. This is also called Bayesian prediction. And doing this, the benefit of doing this, it is less overfitting the training data and is much more robust. So these are several benefits of Bayesian inference. Any question at this?
So MAP, MLE is specific to solve a problem, but Bayesian inference is a concept.
It's kind of a broader framework.
Okay.
So Bayesian inference focuses on the posterior probability, right? So actually, it involves some kind of a debate between the frequentist point of view and the Bayesian point of view. From Bayesian point of view, we consider everything as random variable. So model M is random variable, so it has a distribution. But from frequentist point of view, they just assume data M is kind of a point. And which one is better, which one is worse? There's like a 300 years debate. But in recent years, along with the progress of machine learning and artificial intelligence, more and more people turn to Bayesian framework because it can account for all possibilities of models rather than concentrating on some single point.
And MAP, MLE doesn't belong to Bayesian inference.
MAP can be considered as a special instance of Bayesian inference because it considers the prior. Right? But of course, when you do the prediction, you actually only use one single point. This is actually not fully Bayesian. It's not complete Bayesian inference framework. But usually used to illustrate the influence of the prior. Any question at this point? Okay. So now let us look at as we just mentioned, in Bayesian framework, how does prior influence our model estimation? I mean, how does prior influence the computation of the posterior probability? We can illustrate this problem by looking at this average hit example again. Right? So again, we want to measure the hits, the average hits of the students in the U, and we have a set of data points x1 to xn. and I have set up prior, right? So the prior of the average height is 66 inches, and the standard deviation is 6 inches. And now I define the likelihood of each data point xi, right, given a specific model is another normal distribution, another Gaussian distribution, which is which has the average height m as a mean or as an expectation, and the standard deviation to be 2 inches. So the variance will be 4. So now we want to look at when we compute the posterior probability, how does this part take effect? So we know that, okay, the posterior probability will be proportional to the Pm multiplying the conditional multiplying with the data likelihood. Right? And again, according to the IID assumption, we know this part is the production. Right? Production of the single likelihood for each data point. And now we take logarithm on both sides. We have logarithm of the posterior probability equals to the logarithm of the prior plus the summation of each log likelihood of data point. Of course, here we should plus a constant because here is proportional. And now we can look at this is now we can look at the specific form of the normal distribution. So what is the density for normal distribution? So the density for normal distribution is this form, and I believe in the future you need to recite this formula. So right now you're not required. So this is sigma square. Sigma square is the variance, and exponential to 1 minus 2 sigma square x minus the expectation x squared.
So your normal distribution that has the variance of 4.
Yes.
Are you saying what I'm confused about is the mean? So that m is still the same model?
Yeah.
Right.
Yeah.
So are you saying the mean is the model is the mean, or?
Yeah, the model is the mean.
Okay.
Yeah. Our model is the average height. Average height of the students, say in the U. Our model is a value.
Okay.
Yeah. And so I assign prior of our model, namely the prior for average height, to be a normal distribution, with the mean being 66 inches and standard deviation to be 6 inches. And then I define the likelihood.
So in that case, if the model is just a real number,
Yes, a real number.
are there infinite models that you would have to sort of compare, or?
Yeah, I want to know which model is the best, namely which estimation of the average height is the best.
Okay.
Of course, there could be infinite number of the real numbers. That could be the model. Namely, that could be the average height. Right? But I want to, from the data, to infer the best one.
Okay.
From Bayesian inference, of course, I want to compute the posterior distribution of the average height by observing a set of students' heights. Right? This is our framework.
Okay, and that makes sense, but it seems like finding the probability of the model doesn't seem realistic in a lot of cases. Like to just know the normal distribution of the or know the distribution of the model in practice.
Yeah, finding the posterior probability is usually is a very complicated problem. Usually it's not solvable.
Right, just because if you're not given any data, so the marginal probability of the model.
Oh, you are giving data. Data here. You have a observe a set of students' hits. This is our data.
No, I mean just the marginal probability of the model. So the probability of n in it seems like it seems like in a real sort of machine learning case that wouldn't be likely. That you would just have a nice normal distribution.
Yeah, you are talking about assumption of prior or the assumption of the likelihood.
The assumption of the prior.
Yeah, that's a very good question. Actually, how do you choose the assumption of prior, or how do you define and choose the likelihood is actually a very important question in the machine learning and data science problem. But here, we just make such kind of assumption.
Sure, okay.
Yeah. If you make some, but in this particular case, if you assume both the likelihood and the prior as normal distribution, actually this posterior probability is still a normal distribution. You can verify that after class. It's quite straightforward to verify that. But of course, if you replace it with other distribution, like Laplace distribution, then this form is immediately intractable. Actually, we don't know what is this form.
It would not necessarily be a Laplace distribution, or
No.
that only is the case with normal.
There could be a set of setting for the prior and the likelihood which use the tractable posterior distribution. This is usually referred to as a conjugate family.
Okay.
Yeah, but we won't cover about this concept about conjugation, this kind of things. But yeah, but you're right. You're right. If you choose a more complex prior and more complex likelihood, it is often the case that you cannot derive the explicit form for the posterior distribution. It's a very hard problem. But here we're not trying to explain why it's hard. We're just trying to illustrate how this prior takes effect in computing the posterior probability. Does that make sense to you?
Yeah.
Okay. So let us do some boring mathematical manipulation, right? So here, this is a formula for the density function of the normal distribution. So we simply replace them into the prior and into the likelihood. Right? And what can we get finally? So we can take logarithm. So the prior would be a normal distribution with 66 as the mean and 36 as variance, right? So we just replace the number into here. So we take logarithm over this, 1 over 2 pi. So the sigma square is variance, which is 36 here. And then exponential to 1 minus 2, then variance again is 2 times 36, and then m minus the mean, 66 squared. Right? So this is a log of the prior. And similarly, this is summation of the set of log normal. Right? You can just simply replace it with the density of the normal distribution. So it's pretty mechanical. So it's logarithm of 1 over 2 pi. So in the likelihood, the variance will be 4, right? Because standard deviation is 2 inches, the variance will be 4. And exponential to minus 1 over 2 times the variance again, which is 4. Again, it's for likelihood, right? And then xi minus the mean now becomes the mod m and take square, right? So we can arrange this this terms. It's kind of quite tedious, so I don't want to waste our time to do this kind of things. So let me just write down the results. So it turns out this one to be m minus 66 squared minus plus and over n plus the summation of n xi minus m squared plus a constant. So namely, the logarithm of the posterior probability is like this. So obviously we can say this part corresponds to the prior, right? Remember our prior of the model M has 66 inches as the mean and variance as 6 inches, but it is cancelled. And this part, because it is accumulated through each observations, so this is associating with the likelihood. So what can we observe from this? So you can see this is actually roughly a weighted average, a weighted summation, not weighted average, sorry, weighted summation of the prior and likelihood. Right? So for prior, the weight will be 1/9, and for each data point, its likelihood is weighted by 1. So now from this simple example, we can say how the prior takes effect. It's actually weighted as 1/9 single data point. And how does this weight comes out? This is an interesting question. How does this weight comes out? So I just omit this tedious arranging procedure, but you can repeat it. You can recover it after the class. But I can tell you this weight comes from the variance. Remember in our variance, the variance for the prior is 36, and the variance for the likelihood is 4. So how can we obtain 1/9? It comes from the variance of the likelihood divided by the variance of the prior. This is variance. So this is the weight of the prior. So naturally, we would like to say whether it is possible to adjust the weight or the importance of the prior. Can we make the weight of the prior to be bigger? How can we do that? Yeah, exactly, right? So we can simply, if you increase the variance, then weight becomes smaller, right? Because it's in the denominator, right? Yeah, but we can decrease it. So you can decrease weight to be 39. If we decrease weight to be like a 12, then the weight becomes 1/3. If we can decrease the variance of prior to be exactly the same as the variance in the likelihood, that is 4, then the weight will be 4/4, will be 1. In that case, it means that the prior is actually equivalent to one single data point. So from the qualitative point of view, let us look at why when we decrease the variance of the prior, will increase the weight of the prior. So what does it mean for the prior variance? So we assume this is our original prior. So the variance, the corresponding variance is 36. And it's pretty flat. This flat prior means that we have less restriction for the possible model, right? We'll not have less restriction for the possible model. It actually means that the weight has less influence in model estimation. So you can consider, okay, my prior is very, very large, like 1 million. So it's like a flat line, 1 million. You can consider a variance of 1 million in a normal distribution. It's simply like a flat line. Then, according to our computation, 1/1 million is close to 0. So it means that this variance, it means that the influence of prior can be totally ignored. Then how can we emphasize the importance of variance? How can we make the importance of prior? How can we make the prior more important? Yeah, we decrease the variance, right? When we decrease the variance, what will be the range of the model? Say, it restricts the model much more severely. So actually restrict the model to be only inside this range. That means our model, the estimation model, cannot be very far away from this range. In this way, actually the prior has more impact. And then reflected in this computation, we'll say this coefficient becomes larger. This is a way to adjust the prior of the weight. And the last problem we need to think about is that suppose the variance is fixed, the variance of the prior is fixed, and variance for the likelihood is fixed. Then how does prior's influence change along with the number of data points? Is it possible to change? So let us just put aside the equations. We can consider when you observe more and more data, what's the influence of the prior in the computation of the posterior probabilities? Yeah, less and less, right? It's very intuitive. When I observe more and more data, I think my prior knowledge of my prior bias will be overwhelmed by the information I absorb from external, right? Because I learned so much from data. And now let us verify whether it is valid in the Bayes rule framework. How can we look at it? So we still look at this. This is a logarithm of the log probability, a logarithm of the posterior probability, right? So to look at how the influence of the prior changes along with the number of data points, say when the number of data points increase, this is not very obvious. But we can simply do one thing. We can divide this by n. Right? So this is proportional. So we can divide it by n. And this doesn't change the skew of the log probability. Why? Because when we do the normalization, when it converts to the probability distribution, it won't change when you multiply or divide a positive constant. Right? So for convenience, let us just divide both terms by the number of samples n. So first, let us look at this term. So now this is 1 over n of this summation. So that actually is an average term regarding the data points, the likelihood of data points. Right? So the average will increase the number of data points. Actually, the average won't have much changes on the skew. It could be some perturbations, but it won't have a significant change at the skew. But then what if the prior term? When you increase n, the 1 over n will be 1 over n will be very small. Right? And say when n equals to like 1 billion, then 1 over 1 is almost 0. Then you multiply this prior, which is kind of fixed. Then you can approximately treat it as a 0. And then the remaining term is just an average likelihood term. So remember, no matter how you increase the number of data points, this average won't change much in terms of skew. When n equals to 1, the average could be the skew like 0.4, right? When n increases to like 1 billion, it could still maintain the same skew. It could be 0.39 or 0.49, but it won't be like 0.00001. So now from this point, we can say, when we make the number of data points larger and larger, in our posterior probability computation, actually the effect of the prior is weakened and weakened. And actually, when the number of data points becomes really, really large, it actually converges to the another converge. It's actually you can ignore the effect of the prior, but
Can you predict what n is?
what?
Can you predict what n is?
N is the number of data points.
Can you predict how much you need to make sure you don't need the prior, so you have the correct model?
Yeah, that's a very interesting question. Actually, in many practical problems, the number of data points is not what you can determine. It's determined by the applications. So in some set of applications, the number of data points could be very, very large. But in some set of data points, like for example, if you want to some patients' records for some rare disease, the sample is very, very small. Right? But for very common diseases, the records is very, very large. So actually, for different types of problems, I mean, under different number of data points, you have to design different problems. But here, I just want you to have a sense that how the number of data points will affect the Bayesian inference, namely how to affect the prior. But when the number of data points is relatively small, then the prior takes effect. So this is the main idea. Any question?
So if you have a large number of data points, could you just do MLE?
Yeah, that's a very great point. That's something I want to connect to. So later, when we introduce when we review the MLE, we know that when we do the MLE, we just ignore the prior, right? And now, if we want to do map estimation, when the number of data points is very large, we can see because the number of data points is very large, the effect of prior is ignorable. It can be ignored. So in this way, the map estimation converges to the MLE. But this is kind of asymptotically. That means that map estimation is asymptotically converging to the MLE. This is kind of dynamic. We will increase the number of data points. But if your number of data points is fixed to be very small, they could be very different. Unless you assume, okay, the prior of M is just a constant, it's just uniform. Any questions so far?
How do we get the for the likelihood? The value
This-
for?
This for?
Yeah, I mean number for the.
Oh, this is just my assumption.
Okay.
Yeah, this I mean, in your future like data science modeling, when you model something, you need to determine what is the appropriate number for that. But here, just for example, of course, maybe 4 is not right. Any question? Okay, great. So let us stop today. And probably we will have the first quiz next week.